Hello, future engineers. Welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's one way you can keep me going, inspired, and refreshed. Now, if you find my videos interesting and important to your studies, also please don't forget to subscribe. In this lecture video, I'm going to continue with the distributed forces, line loading or surface loading, and the way of transforming that line loading or computing that line loading into a force, single force with specified line of action. And also part of this lecture video would be to discuss about hydrostatic pressure, and which will be discussed in detail in the course hydraulics or fluid mechanics and hydraulics. So this is just uh, a direct way of discussing hydrostatic pressure because the pressure distribution is over a line or a surface or an area or a point, which is important as an application of the preceding topics on distributed forces. Level 66. The upstream side of an arc dam has the form of a vertical cylindrical surface of 500 feet radius and subtends an angle of 60 degrees. If the fresh water is 100 feet deep, determine the total force R exerted by the water on the face of the dam. So here is the given figure, and based on experience, we had an example similar to this, but it was solved by integration. This time, I used the formula which I also derived or solved in the preceding examples, that the resultant force normal to the projected area of this arc dam is specific weight of water, then Hg, distance from water surface to the centroid of area, times the area. So I'll use that formula here, although we can solve this by integration, but as I said, let's just apply the derived formula in the preceding examples. So this is the projected area. Since this is 60 degrees, this triangle here is equilateral, and this is also 500 feet. So this is the pressure distribution. That's R. That's also 500 feet, and the depth is 100 feet. So Hg or R equals specific weight of liquid, which is water here, fresh water, Hg, which is half of 100, distance from water surface exposed to zero pressure to centroid of the projected area, 50 feet, and the area is 500 by 100 feet. So R 62.4 times 50 times 500 times 100. So R equals 156.0 times 10 to the 6 pounds. So that's the resultant force exerted by water on the face of the dam. Level 67, the semi-cylindrical steel shell of density 7830 kg per cubic meter with closed ends has a mass of 26.6 kilograms. Determine the mass M of the lead ballast, which must be placed in the shell so that it floats in fresh water at its half radius depth of 150 mm. So here is the given figure. Since the semi-cylindrical steel shell is floating, so we have weight, which is quantity mass of lead ballast plus mass of the semi-cylindrical steel shell, quantity times g, so that's the weight equals buoyant force, which is specific weight of water 1000 kg per cubic meter times g times volume displaced. So this is the weight, quantity m plus 26.6 times g, buoyant force 1000 g times volume displaced, so that we can analyze for the volume displaced or which is area of the portion of the semi-cylindrical shell below the water surface times length perpendicular to to this direction, which is zero point 0.6. So that we can analyze the area displaced, we have to draw the end view, which is this, and this is 150 mm as mentioned in the problem. The radius is 300 mm, and let's call that theta over 2. So cosine theta over 2 equals 150 mm divided by hypotenuse, which is 300. So solving for theta, arc cosine of 150 over 300, which is 60 degrees, times 2. So theta is 120 degrees, or 2/3 pi radians. Then this area displaced here is area of sector minus area of triangle. So the area of sector from plane geometry is 1/2 of the radius square, 1/2 0.3 square times central angle in radians, while the area of the triangle is 1/2 product of adjacent sides times sine of the angle included, which is 120 degrees, or 2/3 pi if your calculator is in the radian mode. But if it is in the degree mode, then area displaced is 1/2 0.3 square times 2/3 pi. This must be in radians, minus 1/2 0.3 square sine of 120 degrees. So this should be 120 degrees. So area displaced is equal to 0.05528 square meter. Substitute into this formula, quantity m plus 26.6 times d equals 1000 g times volume displaced, cancelling out g and replacing volume displaced by area displaced 0.05528 times 0.6, then we can solve for m. So solving for m is 6.568 kilograms. Level 68, the small access hole A allows maintenance workers to enter the storage tank at ground level when it is empty. Two designs, A and B, are shown for the hole cover. If the tank is full of fresh water, estimate the average pressure, sigma, in the seal area of design A, and the average increased delta T in the initial tension in each of the 16 bolts of design B. You may take the pressure over the whole area to be constant, and the pressure in the seal area of design B may be assumed to be atmospheric. So because the pressure in the seal area of design B is assumed to be atmospheric, so the atmospheric pressure has nothing to do with the end result. It will just cancel inside and outside. So for part A, this is the design B, which is greater in area than design A. So therefore, the average pressure in the seal area here is equal to the force over the area of design B divided by the seal area, which is area of design B minus area of design A. The shape of the figure is an ellipse, and the area of ellipse is pi AB, pi radius in that direction, then radius in the perpendicular direction. So where A is 0.75, for B 0.75 over 2, for B 0.5 over 2. So again, the force here is pressure at the centroid of area of design B times area of design B. So average pressure is force over force in design B, which is greater, divided by the seal area, which is area of B, area of big ellipse, minus area of small ellipse, which is in design A. So pressure times area of B is the force, then that force should be transmitted to the seal area so that we can compute the average pressure in the seal area. So the pressure is specific weight of water times depth, which is 12 meters. Then the area, of course, area of B is area of ellipse. So it is 9.81 times 12 times quantity pi 0.75 over 2, zero point 0.5 over 2. That's area of B divided by pi 0.75 over 2, zero point 0.5 over 2 minus area of A pi 0.55 over 2, zero point 0.375 over 2. So that's it. That's the average um, pressure in the seal area. And it is equal to 261.6 kilopascals. Then for part B, the average increase delta T in the tension in each of the 16 bolts of design B. So for the second part, we have the force over design A, and this force pushes the area of B, area of A rather, then it causes initial tension in each of these 16 bolts. So therefore, the average increase delta T in the initial tension in each of the 16 bolts of design B would be the force in A, which is pressure in A, 9.81 times 12, area in A, then divided by 16 volts. So delta T equals pressure times area A over 16 volts. So that's the increase in the initial tension in each of the 16 volts. It should be in A because that causes to stretch the 16 volts, because in B there is bigger area and the seal area will hold or partially resist the force on design A. So E 9.81 times 12 times area of A pi 0.55 over 2, 0.375 over 2 divided by 16. So this is in kilonewtons, then divided by 16. So that would be the increase in the initial tension in each volt. So 1.192 kilonewtons per volt. Level 69, the 3-meter plank shown in section has a density of 800 kilogram per cubic meter and is hinged about a horizontal axis to its upper edge O. Calculate the angle theta assumed by the plank with the horizontal for the level of fresh water shown. So this is the uniform 3-meter plank. So the weight acts at the center of gravity, which is 1.5 meters from O and 1.5 meters from this end, half of 3. So weight is density of the wooden plank times G, so it becomes unit weight times area of the end section of the plank, which is constant, times length 3 meters or volume of the plank. Then this part that is submerged, we'll call the length submerged as x, so that's 1.5, and therefore this is 1.5 cosine theta because this is theta. So hypotenuse times cosine of the angle, so 1.5 cosine theta. The distance, horizontal distance of the weight from this pin here, or hinge, axis of the hinge O, because we plan to sum up moments about O later, equals 0. For the buoyant force, let's call this x the submerged length. So the centroid would be at the midpoint of that submerged part, and that's where buoyant force acts, which is specific weight of water 1000 kilogram per cubic meter times G, so that would be newtons per cubic meter, times volume displaced, which is area, cross-sectional area A, which is constant, times length submerged, which is x. And this distance is, because this is theta, is x over 2 cosine theta, or 0.5 x cosine theta. So that's 0.5 x, or x over 2 cosine theta. Therefore, this distance is, because the entire horizontal projection of the plank is 3 cosine theta, and there is already x over 2 cosine theta here. So therefore, this is 3 cosine theta minus x over 2 cosine theta. So 3 cosine theta minus x over 2 cosine theta. Then summation of moments about O equals 0. So buoyant force times quantity 3 cosine theta minus 0.5 x cosine theta equals weight times 1.5 cosine theta. Cancelling out cosine theta and replace buoyant force with 1000 g ax times 3 minus 0.5 x equals weight 800 g area times 3 times moment arm 1.5 after we cancel cosine theta. Cancel out GA also and divide everything by 1000, so that what remains here would be x times 3 minus 0.5x, or 3x minus 0.5x squared, then 0.8 times 3, 2.4 times 1.5, 3.6 on the right side. So 3x minus 0.5x squared equals 3.6. Rearranging, 0.5x squared minus 3x plus 3.6 equals 0. So using the calculators by quadratic formula, so x is 4.342 meters and x is 1.658 meters. Because 4.342 meters exceeds the length of the plank, so it is an absorbed value. Therefore, the acceptable value of x is 1.658 meters. From the figure, sine of theta is 1 meter divided by this length. So this length is 3 minus x. So sine theta is 1 over 3 minus x, and x is 1.658. Solving for theta, theta is equal to 48.17 degrees. Level 70, a structure designed for observation of sea life between the ice in polar waters, consists of the cylindrical viewing chamber connected to the surface by the cylindrical shaft open at the top for ingress and egress. Ballast is carried in the rock below the chamber. To ensure a stable condition for the structure, it is necessary that its legs bear on the ice with a force that is at least 15% of the total buoyancy force of the submerged structure. If the structure less ballast has a mass 5,700 kilograms, calculate the required mass m of lead ballast. The density of lead is 11,370 kilogram per cubic meter. So here is the given figure, and this is the submerged part. So the weight, which is mass of lead ballast plus mass of the structure, quantity times G, equals buoyant force, which is specific weight of ocean water, times volume. Then we have weight of ballast, which is M times volume of lead ballast, then plus the buoyant force, or the reaction here, which is mentioned 0.15 of the total buoyancy force. So we have the weight, quantity 5,700 kilogram plus mass of the lead ballast times G, buoyant force, specific weight of water, density 1030 times G, times volume submerged, which consists of these two parts here, plus volume of lead ballast. Then we have the reaction here, which is at least 15% of the total buoyant force of the submerged part. 0.15 of buoyant force. So for the solution and equation, buoyant force plus 0.15 of buoyant force equals 5,700 plus m quantity times g. So 1.15 buoyant force equals quantity 5,700 plus m times g. So buoyant force is 1030 times g, quantity. So this is the mass of the lead ballast, specific density of the lead 11,370 kilogram per cubic meter times volume of the lead ballast. So substitute it here. Buoyant force is 1030 times g times v sub s plus v sub l. So that's the total volume displaced. Then equals 5,700 plus m, which is 11,370 volume of lead ballast times t. So cancel g. 1.15 times 1030 is, by the way, volume submerged is pi. Radius of this portion of this cylindrical viewing chamber is pi 0.9, half of 1.8.9 squared times 2.4, plus volume of this cylindrical shaft is pi 0.45, the radius 0.45 square, and the depth of submergence is 3 meters as indicated in the figure. So volume submerged is equal to, or volume displaced is 2.5515 pi cubic meter. So substitute here with g cancelled. So 1184.5 quantity 2.5515 pi plus volume of lead ballast equals 5,700 plus 11,370 volume of lead ballast. So from here we can solve the volume of lead ballast. Before that, let's simplify further by distribution. So volume of lead ballast can now be computed 0.37256 cubic meter. So the mass of lead ballast is density 11,370 times 0.37256. So solving for m is equal to 4,236 kilograms. So that's it for this batch of problems.